Now we're going to go into a little bit more details on this theorem that one functions exist if only if kt is mildly Hardner average. So recall that our goal was that because of Yau's theorem, it suffices to construct a weak one function, and that's what we're going to do now. Okay, so here is the construction of the one function. So first of all, I'm going to start off by assuming that we have some constant c, such that the Kolmogorov complexity of any string x is at most the length of x plus c. This is what's referred to as the not invariance theorem. Whatever, what is it called? A triviality about Kolmogorov complexity, which requires the right definition. Anyway, it's true. So we're gonna let c be this constant. This constant depends on the universal Turing machine that we have. Okay, so let us turn now to the definition of one function. So this function is going to take a bit string as input, and what it's going to do is it's going to interpret the first part of that as a program, pi prime, and the second part is going to be an index. So the second part is roughly of length log n, and this is roughly of length n. Okay. Now you see that I'm cheating because the length is supposed to be n, so you need to make the input fit to this thing. This is very annoying to deal with, and I'm not going to tell you about that, but it can be done by using annoying padding arguments. Okay. And this length actually is not going to be exactly log n, but it's going to be n plus c, and this is going to be of length n plus c. But forget about this constant c now. Okay, so think of n and an index I. The next thing we'll do is actually we take this program, and we're not going to consider the whole thing as a program, but we're going to chop it off. And we're going to chop it off after the first I bits, where I was that index. So you take your thing, look at the index, let's say that's 54, then you chop up the first string after 54 bits, and you interpret that as a program. And that's my program pi. And now we're basically done. Now what I'm going to do is just run this program pi for t of n steps, where this is supposed to be a little t. Okay. Run it for t of n steps, and output the output of the program and also the index. You keep the index and you output this. Does the construction make sense? So you really just take your input, you interpret the first string as a program, you're going to chop it off after based on the index you read from the second part, and then you run it and you output whatever you got together with the index. Now the intuition for the intuition for why this should be one way, assuming the hardness of Kolmogorov complexity, is that if I give you a string and your goal is to find the Kolmogorov complexity of this string, if you have somebody who can invert this thing with very good probability, let's say for now you can have someone who can invert this with probability 1. If you can invert it with probability 1, it's very easy. What you do then is you put in your string that you're getting here. You're getting a string that you're supposed to find the Kolmogorov complexity of. You put it in there, and then just try 1, y, 2, y, 3, y, and let this guy try to invert it. If this always inverts it, what it's going to do is to say, like, let's say that you put in 18, y here. To invert it, it needs to find some pretty much pi prime like this, that if you cut it off at 50, I forget what I said, 54, after 54 bits, if you run that for polynomial time, it will output the string y. So if this actually finds a pre-image, you know that there exists a small program that outputs a string. There exists a program of length 54. So if you want to find the smallest program, just start at 1, 2, 3, 4, 5, blah, blah, and output the first thing it outputs. Make sense? So if this thing is worst case easy to invert, then we can actually break KT or solve KT. Now, this might actually not be so surprising because we can do similar things actually for SAT too. There are similar construction for SAT. The surprising thing of this construction is it actually works on average. Okay, so now we're going to reason about why it works on average. So there is something in the structure of this problem that makes it, different from SAT and constructions from SAT. Okay, so assume for contradiction that this is not a weak wave function. That means that we have some attacker that's going to be inverting it. In fact, since it's not a weak wave function, that means that for every inverse polynomial delta, I can find some attacker that will invert it with 1 minus 1 over 1 minus delta. Okay, so I can make it as close to 1 as I want. Polynomially close, inverse polynomially close. Okay, and now what we're going to do is to use this attacker to find a heuristic for KT. In fact, what we'll see actually is that this heuristic will actually solve the constructive version. It's going to find the witness also, in the same way as we did here, right? When we voted, we actually find the candidate. Okay, so here's what the construction heuristic does. The heuristic actually is going to do exactly the same thing as I said before that worked in the worst case. So giving you string y, just try all possible i's. Try to invert it. If inversion works, great. Keep that index and output the smallest one that worked. I would like to make one key observation about this algorithm here that we're going to use later on. Let's say you have some string y, you're trying to find the Kolmogorov complexity string. Okay. If this heuristic actually works when you feed him the true Kolmogorov complexity. Okay, if the Kolmogorov complexity was 54 and you give him 54, y and he inverts it and he successfully finds a preimage, in that case, if A does that, in that case, I claim the heuristic will output the right answer. Can somebody tell me why? Let me repeat again. If A actually, when I feed them the true Kolmogorov complexity here as an I, actually managed to invert, in that case, I claim the heuristic will work on that input.
Because it definitely won't be able to invert on any smaller Kolmogorov complexity, and it's outputting the minimum. So if it
exactly, so on the smaller ones, there is no program, so you cannot invert it. So I don't give a damn what it's doing there. On the bigger ones, I don't give a damn either because they're going to be bigger, so it's not going to output that. Okay, that's the key on observation we're going to rely on. Okay. Now, let's go back to the form proof. Now, intuitively, you would think that if things work with high probability, the same type of argument I did in the worst case should work also. Because maybe we can just do a, if you work with very high probability over all i's, let's just do a union bound because this probability can make it super, super small. It's just a union bound of polynomial many things and we're done. Okay, so you think, oh, it's actually trivial. Fortunately, that argument also works for SAT. So there's something wrong with this argument. And that's actually where things become interesting. The key point here is that we are feeding, the heuristic is actually feeding A, the right distribution of I, because it's, I go over all things, so that's like a random thing, so that's fine. But the why I'm feeding it is not coming from the right distribution. Okay? Because here in the heuristic is getting a uniform string y that it's supposed to find the Kolmogorov complexity of. But in a one-way function experiment, the attacker that's inverting it, he's not inverting it on a random string. He is actually inverting the output of the one-way function. And the one-way function, what is it doing? It's taking a random program of a particular length and giving you the output of a random program. So there is no reason to believe that a random program is going to output a random string. In fact, it does not. If you write the program into Python, it's not going to output a random string. Most of the time, it's going to output this, right? So they are very, very different. At this point, as a cryptographer, like this distribution is far apart, we cannot use this, right? In crypto, we're used to saying like, no, if it works well here, I can make it work on a computationally distinguishable statistically close distribution. But these are not statistically close, they're very statistically far. Everyone's with me? Okay. However, we'll show that using a counting argument, this guy should be made to work anyways. Okay, and the counting argument is actually surprisingly easy, so I'm going to give it to you in 2 minutes, or it will take 2 minutes. Okay, I hope. I'll make one simplifying assumption, just an annoyance. Let's assume that this attacker that is solving the break-in-one function is deterministic. If it's not deterministic, it's more annoying, but it can be done also. Let's ignore that. So let's assume we have an attacker that's deterministic. Okay. And I would like to bound the probability that the heuristic fails. So that's the same thing as looking at now, since the deterministic attacker is deterministic, look at the fraction of y's on which it fails. Okay. Why does it suffice to look at the fraction of y's? Well, because each y here is as common. They all appear with probability 2 to minus n, because I'm picking things at random here. Okay, so if I want to bound the probability this fails, let me just bound the number of y's on which it fails, because each of them happen with probability 2 to the minus n. Okay, so let's consider some y on which this heuristic fails, and we'll try to show that it won't be too many of them. If y fails, if the heuristic fails on y, what did we learn from this key observation? That this case fail. In that case, the attacker A must fail on the input W concatenated to Y, where W is the true Kolmogorov complexity. Right? Because remember, if it works on the true Kolmogorov complexity, then A is going to output a true value, because they don't care about what happens to small ones, because the answer is always no. And then big ones don't care because it's bigger. So if it actually works on W and Y, then I know that the heuristic will work there also. Now, let's look at the probability with which I'm sampling W and Y, and I'm feeding it to attacker in this experiment, in the one function experiment. So the one-way function, remember, it picked the index. That's at random. Okay, so the index is going to be W with probability 1 over n plus c, because we had n plus c allocated for the log n plus c bits allocated for that. Okay, so with probability 1 over n plus c, I'm picking W. I'm picking the right Kolmogorov complexity. Okay, then since I'm doing this truncation, I just need to make sure that given the string y, it has Kolmogorov complexity W. So there exists some short program of length W that outputs a string. Okay, so now I just need to make sure that the first W bits are exactly that program. And that happens with probability 2 to the minus W, right? The length of W. Okay. And since we know that the length W is at most n plus c, I know that this is therefore at least 1 over n plus 2 to the minus n. So what's the conclusion? That the string here that sample the probability 2 to the minus n, if you fail on that, then you must fail here with probability 1 over 2 to the minus n. So in conclusion, if you fail here with probability epsilon, you're going to fail here with epsilon over n. Since I know that I fail here with tiny, tiny probability, this thing needs to be tiny times n. And we're done. Where tiny was delta, right? So therefore here I can fail at most delta times n. And since I can make delta as small as I want, I can make this as small as I want. That's the whole proof. Any questions?
If you want I for n minus order to n, like you have draw I all the way from 1 to like
What?
I'm thinking the simple proof works even if you only draw I from like something very close to n plus. That's
Propensity.
like if I only draw like I for like n minus log n to n plus 3.
Yeah, probably. Because well, I guess it's related to the fact that this actually shows the hardness of the decision version also, where you just need to decide whether it's greater like n minus log n or not. Thanks.
If that's true, wouldn't you get a better like instead of losing a factor of n, you would lose
ABC.
log n in terms of the mildness, like, or is that not the only way where it's coming?
Yeah, let's maybe talk about that later. Yeah, no, it's a good point. I should look into it. But if it's true, that would improve the parameters a little bit. Again, this is not where this is a very tiny loss. The main loss is going from weak to strong. So I guess we haven't really tried to. This is shaping a log n term when you're losing a quadratic term. But, yeah.
So related to what you just said, is this the reason that we have to go from weak to strong? Like we only get a weak one here. Is it just coming from this dividing by O of n thing that you have to do this argument over all the values of I? Like I'm trying to ask like where the
No. To do this argument, I need to make sure that it's like I succeed with very small probability here. And I fail with small probability. Yeah. Any like even a factor 2 loss would be damning. And you cannot get away from even a constant loss, I don't think here. All right, but great question. I think it's very interesting. Okay, so we concluded the first part, which is saying that if KT is mildly hard on average, then we have one functions. Now let's move on to the second part, which is the one that intuitively should be easier, but it turns out to be harder. So we would like to now show that KT is mildly hard on average if one functions exist. And the high-level idea is exactly the same one as we've heard about multiple times already during this workshop. Following Rasmussen, Rudish, Cabret and Kai, and Alan and et al. We start off with a one function, and we're going to construct a PRG. PRGs should be killed by mktp oracle, so therefore we know that one functions can't exist. That's the intuition, right? So we construct a PRG. Remember, a PRG in my context is a cryptographic PRG. This is an object that takes a small seed, outputs a long string, and this string should be computationally indistinguishable from a truly random string by all polynomial time distinguishers. So it's a string that you cannot tell apart if it's the pseudo-random, the output of the PRG, or truly random for all polynomial time algorithms. Okay. And results by Hill show that from one function you can get such a PRG. That's great. And as I said, this mktp oracle intuitively should be able to distinguish these two things because pseudo-random strings have small Kolmogorov complexity, random strings have large Kolmogorov complexity by standard counting arguments, so therefore you can tell them apart. So let's go over it in a little bit more detail, this argument, even though you've seen it before, for everybody who wasn't here before. So uniform random strings by a classic counting argument that you've seen before have, if I take a two n bit string, it's going to have Kolmogorov complexity and also time-bounded Kolmogorov complexity roughly 2n. So with high probability 2n minus log n. Whereas if I look at the output of a PRG that takes n bits and expands it to 2n bits, that's going to have Kolmogorov complexity roughly, or it will always have Kolmogorov complexity n plus order 1. Because to describe the output here, you just need the seed. So these PRGs are very funny objects. It outputs something that looks random, but in terms of Kolmogorov complexity, it's very not random. It has very small Kolmogorov complexity. All right, so let's say we have an algorithm H that can break, that computes KT, and let's see why it breaks the PRG. Well, very easy. Clearly, if you can tell apart small KT or large KT, if the KT is small, then you know that you're here for sure. And when the KT is large, then you know that you're here with high probability. Great. Okay. That's the old argument. I claim that this works very well when you can compute KT with probability 1. But if you have an oracle that only computes KT with high probability, you're in trouble. And let's see why. When I get something uniform, the thing works with high probability, good. Here it's going to output the right answer. Okay. When I give it something pseudo-random, unfortunately, I have no clue what it's going to do. Why is that? I have an oracle that works, let's say, with 99% probability of random strings. How many pseudo-random strings do I have? Basically none, right? They're very, very sparse. So it could fail on all of them, and it would still be an awesome KT solver. As you heard in Valentin's talk, actually, it does actually, if you have a heuristic that is errorless or one-sided error, you can make this argument go through. But what we're looking for is something that is, it can make errors in both ways, and then it's a problem. Okay, so the issue here is that these things have tiny probability mass, and that's why we can't use this argument. But what we realized is actually, if you start off with a stronger PRG, so a more sophisticated object, not just any PRG, but a nicer type of PRG, something we refer to as an entropy preserving PRG, or actually, that's what we wanted to use, but we can't. So we need to use from more complicated objects, something called a conditionally entropy preserving PRG, which sounds like a mouthful. I will try to convince you it's not as horrible as it sounds. But if you use such a thing, intuitively, this is a PRG that makes sure that the output actually has enough entropy in it. And if there is enough entropy in it, even though in statistical distance it's far, because it has to be because it's output of a PRG, you can still use a similar type of counting argument as before to argue that it's going to succeed still. So if the Shannon entropy of the PRG is sufficiently high, you can still make the heuristic work on it. So that's the idea. Okay, so let me kind of introduce this notion. So an entropy preserving PRG is just like a normal PRG, but there's additional entropy preserving property, which just requires that the output of the PRG has high Shannon entropy. And it's kind of, ideally, we'd like to say it has high mean entropy. We don't know how to achieve that. So it turns out Shannon entropy is good enough. And one can show, using a similar style counting argument, a little bit more sophisticated, that if you have an entropy preserving PRG, that actually implies that KT is mildly Hardness average. So KT heuristics do actually eat up and break these kind of entropy preserving PRGs. Why entropy preserving is, or why PRGs don't work, or
why does it work with the entropy preserving?
Yeah, so the entropy preserving ones make sure that there is like a PRG actually in principle can have very, very little entropy, much less than what you want. So you could have like very, 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 very sparse outputs. Okay, and here I need to have something that actually has enough kind of, it's not too sparse in order to get the heuristic to actually work.
But isn't n much more than 2n?
We'll get to it here. So here, what we're going to look at is something that goes from n bits to n plus c log n bits. Okay. You can actually, I won't discuss it here, but to prove this more sophisticated results, you actually need to have ones that are longer. But for the first result, it's going to be enough to consider PRG goes from n bits to n plus c log n bits. Okay. So now the probability mass is pretty big within this, if that is high, and that's the intuition. So can we get these type of entropy preserving PRGs? So the first happy news is that actually this most standard construction of a PRG from one-way permutations actually is entropy preserving. So if you haven't seen these things, this is going to be very fast now, but let me anyway just kind of flash the construction. So this is the Goldach-Levin or Blamicali Goldach-Levin construction of a PRG. You start off with a one-way permutation F. You apply the permutation to your seed. And then you also output an additional bit that is obtained as taking the inner product between some random string R and the pre-image. And this is referred to as the Goldach-Levin predicate. This type of inner product construction has the property that this final bit is indistinguishable from random. And the first part here is not only indistinguishable from random, it is random. So therefore, this thing actually has even mean entropy. This is a great construction. So very nice. The only problem is this starts with a one-way permutation. And we don't know how to get the one-way permutation from hardness of KT. That would be awesome, but we don't. To get a one-way function, we need to use a much more complicated construction. That's what Hill did. They constructed a PRG from one-way functions. But that requires a lot more work. And unfortunately, we don't know if it's entropy preserving. It doesn't look like it. Or at least it's hard to prove that it is. And it's still an open problem how to get the entropy preserving PRG from one-way functions. No, I actually, so I talked to Iftach Heitner, who has these improvements of this, and quite interestingly, he said that this notion of something very similar notion of entropy preserving PRG, they never published anything about it, but it was kind of, they were thinking about that as a stepping stone to get more efficient constructions. And they were trying also for a very long time getting that thing and got stuck. And I don't remember if he had any barriers to it, but there seems to be something that people have kind of, in order to get more efficient constructions on PG, they kind of also naturally, this is an obvious natural occurred kind of. So it seems hard. Yeah, it would be nice to actually, if I could formally prove that it's impossible. Like we don't need it here, but it's still, it would make everything much more nicer and simpler if one could just get it. It's a very natural concept. All right, so what we did to kind of like, if you can't solve the hard problem, just go around it, right? And it turned out that actually you don't need this full power, because these mktp oracles actually can break more funny objects also. Okay, so actually I don't need a full PRG to be eaten by a mktp. It actually turns out to have this conditional PRG. So what's a conditional PRG? It's a PRG such that there exists some event. This event is not computable. Actually, it will be computable, but it's not efficiently computable. But it doesn't have to be computable. Just some event E, such that if I condition this event E, the output of a PRG is indistinguishable from random. And if I condition on event E, then it has a lot of entropy. Okay. And turns out that if I have such a conditional entropy as a PRG, then you can already show hardness of KT.
You need anything about the probability of the event, or?
No, but the event actually will not be too small because of this entropy condition. So it will kind of pop out. So, okay. And then the second thing we can show now is actually using one-way functions, you can get it. Okay, this is going to be super, super fast. Okay, so if you haven't seen these constructions of PRGs, actually what we're going to do is we're going to kind of take like one of the early stages of Hill. This is kind of like a warm-up case of Hill. And even earlier constructions of the constructed PRGs from this object called a regular one-way function. So a regular one-way function is a function where each output doesn't have maybe one preimage, that would be a permutation or injective one-way function, but has a fixed number of preimages. So each output has, let's say, 2 to the R preimages, and R is the regularity. Okay. From regular one-way function, it's actually much easier to get a PRG. And the classical construction of PRG, then you try to do something like Goldach-Levin. Like if I go back to that construction, you apply it to something here, you output your bit. But the problem now is that because of regularity, you're losing, like, this thing might not be random anymore because it's like very compressing. Okay, so what I should do then is just try to like extract out some extra bits from the input. So the construction is take your function, okay? The output of the function has some entropy in it, okay? It actually has n minus r entropy, where r is the regularity. So I can apply an extractor to output and get something random from the output. But that's not enough. I only got n minus r bits. But then the input still has some entropy, in fact, r bits of entropy, because it's r regular. So I can now apply an extractor also to the input. Okay. So this is kind of a method for going from this regular function to something that's basically almost like one-to-one-ish, right? Because I'm applying the function and apply the extractor on the output, and I know how many bits of entropy, how much min entropy the output has, because it's regular. So I extract out exactly what I need, and then I'm losing some entropy from the input. So let me apply the extractor also to the input to squeeze out extra entropy from there. And then finally, I take the Levin bits. So that works if I know the regularity. We don't know the regularity here. So I'm just going to guess the regularity. Okay. I'm going to let I be a guess for the regularity. I mean, that's going to be another input to the function. Now, this sucks as a PRG, because if this I is not correct, well, it's not a regular function. So, you know, it just doesn't work. But the key observation here is that every function, you can actually think of a function as being made up of many regular functions, right? If by restricting the domain to, like, you know, let's look at regularity 1. Okay, let's look at all the inputs that have regularity 1, or we call it degeneracy 1. Let's look at all the inputs of degeneracy 2, blah, blah. So you can think of a function as being made up of a bunch of small regular things. I just don't know which one it is. If I could figure out, I mean, given output, if I knew which one it was, awesome, then I could pick that. I don't know. Okay, I'm just going to pick it at random. Okay. And now if I condition an event that made a good guess, we're good to go. So this is not a PRG at all. It doesn't work as, but it's a conditional PRG. Okay, this was super high level, but hopefully I conveyed the intuition that something can be done there. Okay, and that concludes the second theorem. And as I mentioned, and as we discussed already, you can also state this as a decisional problem. You don't need to view it as this computational problem, but it's also deciding whether the Kolmogorov complexity is more or less than n minus log n. And that's it. Okay, so let's now go back to this Impagliazzo-Wald thing and like really discuss why this characterization gets some implications for Impagliazzo's walls. Okay, and the first one we would like to go back to is to revisit this question of whether we can base one-way functions on MP not equal to P. Okay, so we've now shown this equivalence between these two things, mktp being Hardness average, and you know, if we could just go from MP being hard to mktp being hard, that is proving worse, like MP complete is not mktp. Okay, and then also get a worst case to average case reduction from here to here. Great, we're done. That's all you need to do. Okay, so and the curious thing is that actually Hirahara's awesome work from 2018 does show a worst case to average case reduction going from here to here. So now you're like, well, this is all I need to do, prove MP completeness. Not so fast. Okay, unfortunately, Hirahara only showed a worst case to average case reduction if you define average case hardness using errorless, the errorless notion of average case hardness. And what we need here is Hardness average with respect to two-sided error. Okay, so there is actually kind of a gap, and I personally think that these notions of errorless hardness and two-sided error hardness are actually very, very different creatures. Like the errorless notion seems to really be like heuristic, I would expect there are two types of heuristic out there, really, right? There's weak heuristic and strong heuristic. One is where you have errorless, basically errorless hardness really should be equivalent to worst case hardness. Two-sided error hardness, I don't know yet, okay, if it's equivalent or not. But clearly, like it might be much easier to rule out to get errorless hardness from worst case hardness, even for NP. Now, I do want to point out then, okay, so if you can resolve these two steps, then you have the Holy Grail. But it's also the case now that you need to resolve both these steps, okay? So it's just instructive to just see why you need to do it. If you can base one of your functions on the hardness of NP, okay, then I claim that you need to prove that mktp is NP complete using some non-black box techniques, maybe. Okay, anyone can do that argument for me? Let's say you can prove that you can base, if you can base one of your functions on hardness of NP. So you have a one function oracle, and you know how to use that to solve NP. Now I'd like you to show that using mktp oracle, you can solve NP. Why is that? Yeah, we know mktp breaks the one function, and one function breaks this, done. Okay, and in the same way, you can show that you need to go from here to here. So both those two things need to be done, right? If you want to solve the Holy Grail, you need to prove mktp is NP complete, and you need to go from worst case to average case. So let me again emphasize, this is not coincidental. It's not that these techniques kind of meta complexity here is, an approach towards this. It's a necessary approach, right? You need to do this. That's why I say NP complete in the sense of like non-black box NP complete, right? There's so many different definitions of NP complete, but really let's let go of this like Turing reduction thing. As like I'm define NP complete as using non-black box reductions. That's the right way. Okay, now can we do better, or can we do something different? We'd like to maybe can we sidestep this question of proving NP completeness? No, we can't, because as I mentioned, it's necessary. But maybe we can kind of again try to walk around it and implicitly show it somehow. So in this later work, what we showed is if you instead consider the conditional Kolmogorov complexity problem, then the first step here can be done, actually. You can prove NP completeness of the conditional Kolmogorov complexity problem. Okay, and then the only missing step, and addition, you can prove the same equivalent. This equivalence actually works out directly in the same way as before. So there's nothing to really show here. So you just need to show that this is NP complete. And then afterwards, that means it's only this step that's remaining. Okay. So really, the only thing that remains is to get the worst case to average case reduction for the conditional Kolmogorov complexity problem. So recall, conditional Kolmogorov complexity is the same as KT, but now I'm given an X and a Z, and the goal is to compute the Kolmogorov complexity of X if you get Z as an input. Okay. Now there is a little caveat. The original definition of conditional Kolmogorov complexity was with respect to Turing machines. For our result here, we need a RAM, model of computation. I'm personally not bothered by this. This is anyway the right model. RAMs are better than Turing machines, but it is what it is. It's still open to show NP completeness for Turing machines. Okay, so the first application or first corollary of this thing is what I just mentioned. If you want to base one of your functions on NP notice at BPP, that's equivalent to getting a worst case to average case reduction for mktp. That's exactly what you need to do. Okay. So again, this is another complexity theoretic or meta complexity theoretic interpretation of this Holy Grail. And a second interpretation is the following. If you just want to rule out heuristica, which one is it? Heuristica, yes. No, pestilence, sorry, pestilence, too many names here. If you just want to rule out pestilence, what this means is if you just want to get a construction of one functions from average case hardness of NP, okay, let's not go all the way to the Holy Grail, I just want to show if MP is hard on average, can I get a one-way function? That's equivalent to showing that the uniform distribution is the hardest distribution for mktp on average. So again, let's see why that is the case. Okay, let's say that you can show this, that if mktp is hard for some sampleable distribution, then it's hard for the uniform. Okay, in that case, let's assume that MP is average case hard. That means that there exists some problem in NP and some distribution for which it's hard to decide this language. Since mktp is MP complete, you can now translate this original problem and the original distribution into some new distribution over mckTP, right? Such that mckTP is now hard over that sampleable distribution. If you can go from uniform to, or from any distribution to uniform, then you can go to uniform. And then we have that from uniform is equivalent to one functions. Because this was one direction, and the other direction you can do the same as before. Okay, so really we now have that ruling out Pesiland is equivalent to showing that the uniform distribution is the hardest distribution for mckTP.
Do you have any natural problem where you can actually show uniform distribution is the hardest?
True. They're unnatural.
Unnatural.
Yeah, I think like discrete log, for instance, like anything that has random self-reducibility, maybe. But
Aren't these classical results from the Pagliazzo that show that the uniform is the hardest?
Yeah.
yes, so uniform, but that is like it takes a natural problem, makes it unnatural, what you think, right? So using hashing, you can do these things. But look, the world is what it is. I cannot change it's an if only if. So this is what you need to do.
What do you mean hardest distribution?
Well, like the hardest distribution means if it's hard for some distribution, it's hard for uniform.
You can lose some parameters.
Yeah.
It's,
Yeah, I don't care about the parameters. But yeah.
so the hardest meaning is not exactly.
Yeah. It's hardest. No, it's not the hardest. It's hardest in the sense of like it's like an empty hard. Like
It's complete.
Yeah, it's complete. Yeah, the uniform is complete. Yeah, maybe that's about it. That's it. Yeah. So let me mention like 3 minutes about how to prove this empty completeness. The techniques here are really just borrowing stuff from Rahul Ilango's work, but so I'm going to do it very, very fast, just to highlight like an interesting open problem here. That's so the way you can prove empty completeness on the conditional Kolmogorov complexity problem is going to be exactly following Rahul's work to reducing it from the bounded set cover problem. So here you're giving some sets and some sets over a universe 1 to the n, and the goal is to find a small set cover. Okay, and we know that this is MP hard to approximate. It's a result by Trevisan. And what we want to do now is take this set cover instance and turn it into a Kolmogorov complexity instance, such that if the set cover is big, then the Kolmogorov complexity is big. If the set cover is small, then the Kolmogorov complexity is small. The conditional Kolmogorov complexity. Okay, so so following what Rahul did, we're going to first replace each element in the universe by a random string. A random string, which therefore is random, so it's going to have large Kolmogorov complexity. And now we can think of a set here as being described by a string that contains the elements from the universe. So if this is the universe, each string here now is replaced by a random string. Now this set S1, which is 1, 3, is going to contain this string and this string. And 2, 3 contains this one and this one. Okay, that's step 1. And now intuitively, what we're going to do is we're going to ask This is going to be the string we'd like to find the Kolmogorov complexity of, the whole universe. You'd like to recover all these n strings, or n times m strings. Each string is of length m, and there are n strings. Okay, so it's a string of length n times n. What Rahul did was he considered his oracle problem, and he put all these sets inside different oracles. And the idea now is that if you know a set cover, then you can just point to some of these sets, and that's a way to summarize this string in a very succinct way. So if you have a small set cover, I'm not pointing to this, this, and this. Good. Now we're just having the indexes of the sets. You can compress the string. Since we don't have access to oracles, we need to somehow put these sets into the auxiliary input. Okay, and what we'll do is just take these sets and put it into random position in auxiliary input. Okay, and I'm going to now use the fact that the auxiliary input is much, much longer than the running time of the Kolmogorov complexity, the T in the Kolmogorov complexity. So if you don't know where to look, you can kind of not figure out where these things are in the string. So really think of this as kind of an information theoretic way of obfuscating these oracles that the whole is using. I'm just placing it into random position. It's a very long string. So you can, if you have long time, you can just enumerate it and just find where they are. Okay. But if you don't have that time, then you can only do it if you know, like you can specify where they are if you have a set cover.
That's where you need RAM.
That's where you need the RAM. Exactly. So that's where you need the RAM. And so the reason I wanted to mention this, so basically, yeah, the Z is so long that if you're time bounded thing, you cannot figure out where they are because you're just going to look at random positions. It doesn't really help you. Okay. And okay, so the reason I wanted to mention this, even though this is really very high level, and it's really mostly based on our own work here, is that there is a very upsetting reason to have this long Z, because there is a more recent work by Hirohara that shows that if you can make this Z small, you can use symmetry information theorems. Remember from earlier talk, the symmetry information is a way to relate conditional Kolmogorov complexity to unconditional, right? So if you can actually do this, to relate unconditional to unconditional, then you have also shown MP hardness or MP completeness of the unconditional one, the normal one. Okay. Unfortunately, this symmetry information style thing will only work where Z is short. So if you can do this kind of obfuscation here in a more succinct way, where the string is not very long, then you've actually shown MP completeness of mktp. So I think that's a very, very clear open question, and it's like maybe doable, and that would be a very clean way of getting towards getting MP completeness of mktp. All right, so to sum up what we've seen so far was that the first result was mktp is complete for one functions. So mktp is one function complete. So that means that if you want to go from here to here, you need to show that mktp is MP complete and a worst case average case reduction for this. And now using the conditional inversion, we got the following two things: that if you want to get this result, you just need a worst case average case reduction because it is MP complete already. And additionally, that the uniform is complete for in average case cells. Okay, so those are two implementations. We still have this thing left here of like, how do we go from here to here? Okay, and the way that's going to be done is by showing actually that you can get characterized one functions from mk little tp. Okay. So let's recall what this mktp was with little t. So this is this Levin notion of Kolmogorov complexity. And the Levin notion of Kolmogorov complexity is of a string x is a length or the cost of the cheapest programmed output string, where you define cost as adding up length plus logarithm of the running time. So I'm looking at the cheapest program that outputs a string x, where the cost of a program is the length of it plus the logarithm of the running time. Now, we've already, or not here, but in earlier talks, what we heard about was that this problem actually is very different from mktp with t's above, because it's not in NP, it's X complete with respect to non-uniform reductions. Okay, so what that means is what was shown before was that if X is not inside P/poly, in that case, mkt little tp is not in P/poly. So what we observed was that actually you can show something stronger. You can show that if X is not equal to BPP, then this problem is also hard for BPP. And not just hard for BPP, it's actually average case hard. And this is just by using exactly the framework that Valentin was talking about in the CIKK paper. So you can actually get from this assumption that XP is not inside BPP to errorless hardness for BPP. Okay. And the next thing we can show, and this was done independently by us and also by Hanlin and Rahul, that two-sided error hardness of mktp actually is equivalent to 1A functions. Okay, in one direction, this previous the PRG proof that we did works directly. In the other direction, you need to tweak the proof a little bit. I'll maybe mention 2 words about it. So in fact, in the remaining few minutes, let me very high level kind of again sketch this argument that you've seen many times, but I think it's really nice to drive home again. This is really just a CIKK style argument, because it kind of explains why normal PRGs actually can be broken by a errorless algorithm. Okay. Okay, this is okay, but the conclusion then is like if you want to base one functions on x not equal to VP, that's equivalent to showing actually something weaker than what I mentioned in the slide. The only thing you need to do is to show a reduction from errorless to two-sided error hardness. Okay. So this really is these notions are really super different. Errorless hardness and two-sided error hardness are crazy different, because if you can do that, you haven't just shown the Holy Grail. You've shown like the super Holy Grail. You've shown how to get like crypto from X not in BPP, and X not in BPP is true. Okay, that one. NP versus P, I don't know, but that X from BPP, like that's yeah.
The two-sided hardness, that's a uniform distribution, or that's some.
Yes, uniform distribution, uniform, yeah.
And same for the errorless.
Yes, uniform, yeah. All right, so let's go over CIKK style argument again here. So the key lemma here we show is that if you have an inefficient PRG, and this is something you can get from the assumption that X is not inside BPP using the Impagliazzo-Widgerson construction. So Impagliazzo-Widgerson show that if you have X not in BPP, then you can get an inefficient PRG. Now I'd like to use such an inefficient PRG to show that mktp is errorless hard. And same argument as before. We want to distinguish between uniform and pseudo-random. We have a little bit more. Now we're looking at mktp, and mktp actually is good because it can also kill inefficient PRGs, as long as they're just running sub-exponential time, because I'm charging logarithmically for running time, and that's kind of what's so cool about the mkt Levin Kolmogorov complexity. As long as it's sub-exponential running time, it's fine, because you're only going to add this little less there. Okay. The problem here, as we already discussed with PRGs, is that heuristic doesn't always work, right? If it worked always, it would be done. That's the previous proof. But it might fail, okay? And in the uniform, we know it works with very high probability, and we know it's going to output 0 with high probability because it's uniform, it's a right distribution. That's what it's supposed to work on. But when I give him outputs of the PRG, I don't know what it's going to do. Okay, it might fail on all of them. But if this is an errorless heuristic, we know that it's either going to give the right answer or a bot. right? That's what the errorless thing does. It never gives the wrong answer. It just says, I give up. And the key point here is that if this guy gives up, then you can always say that it's pseudo-random, right? Because then you know for sure you're going to succeed. When it's pseudo-random, you always get the right answer. When it's uniform, you're still only going to lose a small probability. So this whole approach still works when you have errorless hardness, and that's okay. The next step, what I really don't have much time for, was if you looked at the original PRG construction, you needed to run the program for T of n steps, and the T of n came from the running time bounded money function. When we deal with mktp, we don't have a running time bound. We don't know the running time. So how long should we run this function? That's a problem, right? And so let's say we run it for some T of n steps for now. And let's modify it. So I'm going to output not the index as I, but I plus log of the actual running time. Okay. What you can show now is that actually going to work. It will work as long as the running time is actually at most this. Okay. But the problem is when it's longer than that, what do we do? It's an issue. Okay. So sometimes it could be, since I'm doing with this mktp, it could be that the shortest programs running time is exponential, right? With mktp, that could happen. So we refer that as the KT witness. Is the shortest program actually the witness is the Kolmogorov complexity. It turns out you can show using a very simple lemma, very simple statement is that actually most strings doesn't happen for most strings. Most strings have a KT witness with small running time. And if I know that most things have a small running time, I can just cut it off at that, and then we're done. Okay, so I'm running out of time, so I'm not going to tell you about that. But the proof is this, it's the one-liner. Well, 3 on slide, but 1 in the paper. So, all right, so summing up, now we kind of seen this whole picture. Tali is going to tell us more about this thing. And let me just, what's outside here. Let me now, unfortunately, running out of time, but I wanted to mention a little bit more about this uniform being the hardest here. Okay, so as we said, if you wanted to rule out Pesiland, you want to, it suffices here to show that for mktp, you can go from any distribution to uniform. So the question is, can you make any of these things work for any distribution? And there is this very nice recent result by Ilangoran and Santanam that actually shows a different characterization of money functions using the hardness of K complexity. So not the time-bounded one, but the unbounded one with respect to any distribution. So they stated this as a gap problem. They said distinguish between large and small Kolmogorov complexity for certain polynomial time computable bounds that are sufficiently far apart. If there exists some distribution for which this is hard, that's equivalent to the existence of one functions. So with Yanyi, we had kind of rephrasing of this thing. You can say that one functions exist if and only if just approximating KT is hard with respect to an efficiently sampleable distribution. This really is a rephrasing of what they did. So this is very nice because now it's with respect to any distribution, right? If one functions exist, then KT is hard for some sampleable distribution, and if K, sorry, not KT, but K, and if K is hard for some efficiently sampleable distribution, then one functions exist. And the proof is actually very easy. It's here, and in my remaining 1 minute, I'm going to give you it because it's very instructional. The first direction is you want to show that if one functions exist, then K is hard for some distribution. And remember, we had to work very hard for that before, okay? But now I just need to find some distribution to do it, not the uniform one. And then it's trivial because from one function you go to a PRG, and the PRG defines a distribution in which the distinguisher, like this K oracle, actually works, because I can, with 50%, I'm going to be uniform, 50% the PRG. So that's actually, if you succeed with high probability on that distribution, then you can tell that's exactly what it means to tell them apart. So if I can pick the distribution, very easy to prove that step. And the second step, which is the interesting one, you want to show that if K is hard for some sampleable distribution, then you get a 1A function. And that's going to rely on results by Impagazzo, Levin, and Luby, both actually, that show that if 1A functions don't exist, then we can do approximate counting, and in fact we can estimate the density of the probability that something was sampled with. So if I sample some string x from some efficiently sampleable distribution, if 1A functions don't exist, you can find out what was the probability of this string being sampled. Okay, that's what IL square say. And now let's use this probability estimator to compute Kolmogorov complexity. And this actually now will follow directly actually from the coding theorem, actually, that was already mentioned, that said that, look, if I know the probability of sample, that's actually going to be your Kolmogorov complexity. Okay, so what you should just do is just take the probability, or sorry, the logarithm of the probability is your Kolmogorov complexity. And the key, yeah, the argument is here, but it's one direction is the coding theorem, which is particularly easy in this setting, and the other direction is counting. So just doing this thing and computing the logarithm of the density, that's actually going to give you an estimate within log n, because you lose a little bit here because you don't have this prefix-free definition. So you lose log n or some log n's, but that gives you the Kolmogorov complexity. All right. So it's very nice because now it really it works for any sampleable distribution.
Well, you have -3.
-3, yeah. Minus log n is good enough for me. I don't care about prefix free. Okay, so it's really cool. It works for any. What's less cool is that it works for any. Okay, so let me explain this, because this is a kind of, the fact that it works for any seems like a great thing, but actually when you look at what happens here, the fact that it works with any, it really, what happens here is the distribution is the 1A function, right? So this says, what IL say really is that, look, if this problem is hard for some distribution, then this distribution must be a 1A function. So in some sense, you're saying if 1A functions exist, then I know a distribution, because I can get using a PRG, I can get some distribution. But if this problem is hard for some distribution, and distribution is the 1A function itself, so it doesn't really give me an insight into how to find this 1A function. And that's very different from before, when we had, it was a concrete problem. So here it's not a single problem. Really, we know there exists an element in the class, but that element is actually specified by the 1A function. Okay, so that at first looks like annoying, but maybe there's still an approach from this to rule out Pessyland. Because if I only want to do is to rule out Pessyland, let's say that NP is hard on average. Okay, there exists some distribution for which NP is hard. If I can now take that distribution and turn it into a distribution for K, that would be great, because then I have 1A function. And we know that K is RE complete, right? So after all, this really should be easy to go for, like, K clearly is RE complete. Clearly, you should be able to solve NP complete NP problems, right? And indeed, one can get these kind of reductions. Unfortunately, this approach was kind of like, it seemed very promising now, but Santaman and Sachs showed that actually you cannot have a non-adaptive reduction from MP to K. Okay, and really, if you want to go, if you want to make this step work, that if MP is hard on average, then K becomes harder than average for some distribution. You need this reduction to be a non-adaptive reduction to say that like my distribution here, I would like to get the distribution there. To do that, I need to have a non-adaptive reduction. And unfortunately, those things are not possible. But maybe one can still somehow overcome it. Okay. All right. So in that case, I'm going to sum up and say that my conclusion here is that we've seen is that actually understanding in Pagassi's words, at least in order to get one functions, necessitates Kolmogorov complexity. This is an if only if. You really need to understand these questions in Kolmogorov complexity. There's been a lot of amazing progress in the last few years, and there are lots of new papers coming out. It's very exciting. I also wanted to mention that this has applications also to de-randomization. We didn't have time to get into that, but maybe Yanni will talk about that in later on. So you can get Kolmogorov complexity characterizations of what it means to BPP versus P question in particular. That's why I define this new world randomalia. If you want to understand randomalia, we also can do that using Kolmogorov complexity. And let me end with Frank Zappa.
Any super quick questions? By the way, I'll make up the time in my talk. Questions?
Thank you.